Okay, here are solutions for perfect problem 5 from Math 251. We're given these two problems. Really, they're four problems, but anyways, we're given these problems, which are going to be tough to fit in on this page. The first thing to do is to show that these derivatives are true. Show that the derivative of arcsine is 1 divided by the square root of 1 minus x squared. Do so using implicit differentiation. So the idea there is set up an equation. So instead of trying to think about this as the derivative of this arcsine of x thing, think about an equation y equals the arcsine of x. And if we could just find y prime, essentially we'd be finding the derivative of arcsine of x because y is arcsine of x. But by setting it up as an equation like this, we can manipulate the equation before we take the derivative. Because we can't take the derivative since it says arcsine of x, since we don't know the derivative of arcsine of x, we're trying to prove that. But we could take the sine of both sides of the equation so that we could rewrite this as sine of y equals x. Take the sine here, the sine here. The sine of the arcsine of x is just x. And now I can take the derivative of both sides of the equation. This is using implicit differentiation. So the derivative of sine of y, well, the derivative of sine of x would be cosine of x. So the derivative of sine of y is cosine of y times y prime. Doesn't look like it, but that's actually the chain rule going on there. The outside function is sine of x. The inside function is y. Y all by itself is a function. So I take the derivative of the outside part here, multiplied by the derivative of the inside part here. So I can now solve for y prime. It's just 1 over the cosine of y. But it's strange to define y prime in terms of y, since y is just something I created. So instead of 1 over the cosine of y, maybe I'll write it's 1 over the cosine of arcsine of x, because up here I say y equals arcsine of x. It's a good answer. It's not a great answer, but it's okay. The derivative is 1 over the cosine of the arcsine of x. That's true, but that's not what we were trying to show it was. This is equal to this. This is just a simplified version of it. So what I'm now going to do is I'm going to simplify this guy. But I want you to note that we're done with the calculus. This is all trig stuff. We're going to simplify the cosine of the arcsine of x. And the way we'll do that is by substitution. So I'm going to let t be equal to the arcsine of x. I'm going to take the inverse trig function that's on the inside of this function composite and give it a name, t. Why that's useful is now really all I'm trying to simplify is the cosine of t. And I have information about t over here. Since t equals the arcsine of x, I know that the sine of t is equal to x. Instead of x, I'm going to write it as x over 1. Because if I have it written as x over 1, it's easier for me to draw a picture. Draw a right triangle. That's a horrible right triangle. Try again. I don't know if that's any better, but whatever. There's a right triangle. Pick anywhere I want for my angle t. And using SOHCAHTOA, I know that the sine of this angle is equal to the ratio of the opposite over the hypotenuse, the length of the opposite and the length of the hypotenuse. So if sine of t equals x over 1, I can make this x and this 1 right here. So I have this picture that gives me all this information about t. I just want to figure out the cosine of t. Remember, that's what I'm trying to simplify over here, was the cosine of what I'm calling t. And I could do that if I just knew this one side right here. Fortunately, I can figure out this one side right here using the Pythagorean's theorem. I know that a squared plus b squared equals c squared. So this thing squared plus this thing squared equals 1 squared, which is just 1. If you solve for this thing, you'll get the square root of 1 minus x squared. So then I can say, well, the cosine of an angle is just equal to the length of the adjacent side over the hypotenuse. So it's the square root of 1 minus x squared. That's what the cosine of the arcsine of x is. So what I can say is for my final answer, maybe up here, is that y prime is equal to, instead of 1 over cosine of arcsine of x, I can say it's 1 over this square root of 1 minus x squared thing. There you go. All right, do that again. This one's even a little bit more difficult. Maybe I can go a little quicker. Same idea. Now I'm going to make y equal to the arc secant of x. And I'd like to take the derivative of both sides. I want to find y prime again. But I can't initially take the derivative of both sides because I don't know the derivative of arcsecant of x. I could take the secant of both sides of the equation. And now I can take the derivative of both sides. The derivative of secant of y, well, the derivative of secant of x is secant of x times tangent of x. So the derivative of secant of y would be secant of y times tangent of y times the derivative of y, because y is itself a function, y prime. And that's equal to 1 because the derivative of x is just 1. So I can solve for y prime as 1 divided by secant of y times tangent of y. Which is great, but I don't want to leave y's in my derivative. So sure, right here, I'll change all my y's into what y is equal to. Y is equal to arcsecant of x. So what I get is the secant of the arcsecant of x times the tangent of the arcsecant of x. Rewrite this over here, save some room. Maybe I'll rewrite it up here. 1 over secant of arcsecant of x. Wait a minute, isn't that just x? Yes, give me a second. Times the tangent of the arcsecant of x. And that was all just substituting in anywhere I saw the letter y, I changed it to arcsecant of x, because up here it says y equals arcsecant of x. I need to simplify two things now. Over here I only had to simplify one thing, namely the cosine of the arcsine of x. Over here I have two of them. Fortunately, one of them works out really nicely. The secant of the arcsecant of x. Secant and arcsecant are inverse functions, so when you compose them together you just get x. So all I got to figure out is what is the tangent of the arcsecant of x. Maybe I'll do this down here. Let's simplify. Tangent of arcsecant of x. I'll get that answer, I'll write it right here, and I'll be done with the problem. So to simplify the tangent of the arcsecant of x, we're going to create two columns like we did before. What I'm going to do is a substitution. I'm going to let t be equal to the arcsecant of x. Whatever the inverse trig function is what you want to make t. So that allows me to simplify immediately. Just say my answer is just tangent of t. Instead of tangent of arcsecant of x, it's tangent of t. I'll be able to simplify that once I get some information about t. To get my information about t, I'm going to take the secant of both sides of this equation. That gives me the secant of t equals x, which I'm going to write as x over 1. Then I draw a triangle. Using SOHCAHTOA, I know that the cosine is the ratio of the adjacent side to the hypotenuse, and I know that the secant is 1 over the cosine. So if cosine is adjacent over hypotenuse, secant must be hypotenuse over adjacent. So now my picture looks like this if I'm throwing t right here. I want to figure out the tangent of t. I want to figure out tangent. Well, tangent is opposite over adjacent. I need to know this side right here. I can figure out this side using the same method I did up here. I know that this squared plus this squared has to equal this squared. So if I solve for this guy, I would take this x squared minus 1 and take the square root of it. What I would get, maybe in a different color, using the Pythagorean theorem. How about that? Using the Pythagorean theorem, you can get that this is x squared minus 1 square root. And now that I have all the different sides of my triangle, I can figure out the tangent of t. Tangent is just the ratio of the adjacent side to the, tangent, SOHCAHTOA, the opposite side over the adjacent side. So tangent of t is just the square root of x squared minus 1 divided by 1, aka the square root of x squared minus 1. This is the tangent of the arcsecant of x. So up here where I had tangent of arcsecant of x, I'll just write square root of x squared minus 1. And what I'll get is the derivative I was hoping for. All right, 2 more problems, although I think these last 2 will go a little bit quicker. Sure. So this is 1. This was also 1. 1a, I guess. This is 1b. 2a asks me to find, looks like 29, asks me to find the derivative of something, and that something is, I'm going to color code this, the arcsine of something. What do you want me to take the arcsine of? Of this thing, 1 divided by the square root of 1 minus x squared. Okay. 1 divided by the square root of, kind of running out of color, so I'll recycle, I'll go back to blue, 1 minus x squared. With these colors, maybe you can see a whole lot of chain rule going on here. I got this outermost function, the arcsine of something, and then to figure out that derivative of that something, I'm going to have to use some other rules. The challenge with this problem is that the function that's being composed with arcsine of x is the derivative of arcsine of x, which makes it hard to keep track of what goes where. But let's give it a shot. The derivative of arcsine of this thing. Well, the derivative of arcsine of x, I know, is 1 divided by the square root of 1 minus x squared. But I don't want the derivative of arcsine of x, I want the derivative of the arcsine of this stuff. So I'm going to say 1 minus 1 over the square root of 1 minus x squared. Leave all this stuff alone. What I've now done is I've taken the derivative of the red layer. Now I'm going to look at the green layer. For the green layer, what I want you to note, what will make life easy, is knowing that 1 divided by the square root of something is the same as that something raised up to the negative 1/2 power. So I could take that negative 1/2 and bring it down in front, and then subtracting 1 from the exponent, I get negative 3/2. This is what I would get with an x in here if it were x to the negative 1/2 power, but it's not. It's 1 minus x squared to the negative 1/2 power. So I'll leave that 1 minus x squared alone, take the derivative of the negative 1/2 power part of it, get this, and then I'll multiply that by 2x, by negative 2x, sorry. Why negative 2x? Because that's the derivative of 1 minus x squared. It's the sum of two things. The derivative of 1 is just 0. The derivative of negative x squared is negative 2x. Mess right there ends up being our answer. Yeah, whatever, good enough. I was thinking that might be hard to read, but what are you going to do? All right, one last problem. Now we want to know the derivative of arcsecant of something. What is that something? Well, it's kind of a mess. It's, maybe I'll rewrite it here. It's x to the negative 1 power times x squared minus 1 to the negative 1/2 power. Might seem like a weird way to write it, but I think that'll make life easier. This x, since it's down on the bottom, I can make it x to the negative 1, and then x squared minus 1 is raised up to the 1/2 power. That's what the square root does. But since it's down on the bottom, it's to the negative 1/2 power. And I think by writing it like this, it'll make life a little bit easier. Let's see. The derivative of arcsecant of something, kind of screwed up my color coordination. Derivative of arcsecant of something is 1 divided by that something times the square root of that something squared minus 1. And in each of the parentheses, I'd have an x if it were just asking me the derivative of arcsecant of x. But it's not. It's asking me the derivative of the arcsecant of all this stuff. So inside each of these parentheses, I'm going to write x to the negative 1 times x squared minus 1 to the negative 1/2. Try that again. Same thing here, x to the negative 1 times x squared minus 1 raised up to the negative 1/2. And now I'm not done. I have to multiply that by something. And since I'm low on room, I'll take advantage of arrows. Well, what that something is going to be is product rule. Trying to take the derivative of the stuff in red here. Well, it's this times this. The product rule tells me the derivative of something times something else. The derivative of f times g is f prime. The derivative of this guy, which would be negative x to the negative 2, times g, x squared minus 1 to the negative 1/2, plus g prime, the derivative of this guy. Well, let's see. Looks like I got a chain rule going on. The outermost function is stuff raised up to the negative 1/2 power. So I'll bring that negative 1/2 down in front. Leave the x squared minus 1 alone. And then subtract 1 from the exponent to get to the negative 3/2 power. But then I'm not done. I have to multiply that by the derivative of x squared minus 1, which is 2x. F prime times g plus g prime times f. Something like that. All this stuff is in parentheses and gets multiplied by this up here. You could absolutely rewrite this if you felt like it. I don't think I feel like it. I think I'm going to leave this answer just like this. Maybe I'll throw a couple boxes. Well, I don't even know if that helps. I'm just going to leave it just like this. Those are my answers. That's the end of this video.